Okay, we shall now continue from where we left just now in the last lecture, lecture 5a, where we take stock of what we have calculated, which is the velocity A and velocity B and omega AB and omega OA. And now we need to find the acceleration. So in the question, we were asked to look for the acceleration of point A, point B, and the angular acceleration of link AB and angular acceleration of AO. And what are the data that we have so far? It would be good if we can write it down somewhere, and I think this is a good place where we can write down our results that we obtained before, which is omega OA. We have the answer for omega OA, which is omega OA is 20 over 8k, and then omega AB is minus 15 over 6k. All these are in radian per second, of course. And then do we have any other thing we need? I think that's all we need. And then we have VA and VB. VA is VA. Have we got VA? Yeah, VA is minus 20i. Somewhere here we write minus 20i. Yeah, and then we have VB. And then VB is minus 15j minus 20i. Yeah, so we already added all the answers that we obtained. This is from the original questions. The green one are from the original question. These are the one that we answered from the velocity component. So now we are ready to tackle the problem associated with the acceleration component of A and also the associated angular acceleration of alpha AB and alpha OA. And let's look what kind of equations that we can use. We know from our observations before that we can find the acceleration of A relative to C. Yeah, we know from before that the acceleration of A relative to C is given by the acceleration vector of A relative to B plus acceleration vector B. And this is particularly true because C and O are taken as not moving, so we will just, in this case, because there's no link, so we say it is equivalent to A relative. Oh, I just read it together just to make sure that the students can follow the logic of the argument, and then we can just write it AA equals to acceleration A relative to B and acceleration B. Now, because the acceleration terms are very long, I have to be mindful of the space that I have to write all these things. So we'll do it slowly and see whether we can solve the problems within the space that we have. So we know that acceleration of B is equivalent to acceleration of B tangent plus acceleration of B normal. Yeah, so I'm gonna cut down the whole process, and I said, well, the tangent component will combine it just together. So the tangent component is alpha AB cross position vector B relative to alpha BC. This is BC, yeah. Position vector B relative to C, that's the tangential component, minus omega square. The normal component is minus omega square position vector B relative to C. That is the formula for tangent plus normal. So in this case, alpha is given by 2k. Alpha is given by 2k. We know that alpha here is 2k. So it's 2k cross position vector B relative to C is minus 3i plus 4j cross minus 3i plus 4j, and then we have omega. Omega is 5, the magnitude is 5 square, and position vector is minus 3i plus 4j. Yeah, so now we have 2 times 3 is 6, k cross I is j, so minus 6j. 2 times 4 is 8 plus 8. K cross j is minus I, so I minus. Okay. And then we've got this minus 25 times 3 is 75, minus minus is positive, 75i. Minus 5 times 4 is minus 20. 25 times 4 is 100, minus 100j. So we can now safely write that A, the acceleration of B, equals to minus j minus 100. This is minus 8 plus 75. 75 plus 8 is 67. So 67i minus 106j meter per second square. So that is the acceleration of B. Okay, we need now to move to acceleration of A. Yeah, so what is the acceleration of A? So similarly, acceleration of A has two components, A normal, and A normal, and acceleration of A in the tangential direction. And this can, normal is minus omega OA square times the position vector A relative to O. Yeah, and then the tangential is alpha OA cross position vector A relative to O. So in this case, we know what omega OA is. Omega OA is, from the previous answer, is 20 over 8k. So it is minus 20 over 8 square. And then we have position vector A relative to O is 8j. Yeah. And then we have alpha OA. Since we do not know what alpha OA is, this is unknown. We have to assume unknown, therefore assume. What do we assume? We assume that alpha OA is equivalent, the vector here is equivalent to alpha OA k cross the position vector, which is again minus 3i plus 4j. Yeah, so we have then something like minus 400 over k, so minus 50, yeah, 8 to 400 divided by minus 50j plus and then k cross I is j, so alpha minus 3 alpha OA j, and then k cross j is minus I minus 4 alpha OA I. Okay, so we have got this. So we can now somewhat simplify. We can now somewhat simplify the expression of A as minus minus 50 minus 3 alpha OA J, then minus alpha OAI. Yeah, so that is the vector A, acceleration of A. So we have solved acceleration of B, we have solved acceleration of A. We now need to find acceleration of A relative to B. So the acceleration of A relative to B can be written as two components. Again, alpha, again I'm going to A relative to B, tangential plus acceleration of A relative to B in the normal direction, and the tangential is alpha AB, and we don't know about it, so we assume alpha AB K cross position vector A relative to B. Yeah, similarly for the normal component is minus omega square position vector A relative to B. Now alpha OA vector position vector A relative to B is quite straightforward. It is A relative to B is minus 6i. So alpha AB K cross 6i minus omega AB. What is the omega AB? We have calculated omega AB before, and it's minus 15 over 6. 15 over 6 square, and then position vector A relative to B is 6i. A relative to B is minus 6i. It is 6i. So it's minus 6i. Yeah. So negative and negative become positive. So K cross I is J. So 6 alpha ABJ. And then 15 over 6 is 15 over 6. I don't have. It will be like 15, 150, 155, 75, 2 to 5. So 2 to 5 plus, yeah, plus 2 to 5 over 6i. So that is the value of acceleration A relative to B, the vector. So we now have all the components: acceleration B, acceleration A, acceleration A relative to B. Now we can write the big equation, which is acceleration of A. That was the equation that we started to write before, that A equals to acceleration of A relative to B plus acceleration B. So we rewrite that again, and we will now have acceleration. So we will now rewrite acceleration of A equals to acceleration of A relative to B plus acceleration of B. And then we'll now start to plug in the value. So A, we know what A is, minus 50 minus 3 alpha OA J minus 5 alpha OAI. Okay, then alpha AB, yeah, 6 alpha ABJ plus 2 to 5 over 6i. This is one component, plus, don't have the space here, so I'll just bring it down. We have AB, and AB has calculated, we have calculated AB before, is 67i minus 106j. 67i minus 106j. Yeah, so we might want to simplify the whole expression so that we can manage it better. So I'll just do it on the right hand side. This is equals to 6 alpha AB minus 106J, yeah, and then plus 225 over 6 plus 67I. Okay, so when you can now compare the I component, yeah, on the right hand side the I component is minus 4 alpha OA equals to 225 over 6 plus 67, and then you can get alpha OA equals to all this expression, okay, and then you can get alpha OAK equals to negative something, okay, radian per second square. So you can solve this 225 over 6 plus 67, and then you can get this alpha OA as a function of something here. And similarly you can get alpha AB from the J expression, okay, so so there is no so there is minus 50 alpha A 67 minus 50J minus 3 alpha OJ. So minus 50 minus 3 alpha OA J, yeah, is equivalent to 6 alpha AB minus 106. Now, because you know the value of alpha OA from here, yeah, therefore you can substitute the value and you can get this alpha AB equals to minus 50 minus 3 alpha OA, yeah, and then plus 106 and then divided by 6. That is the solution for alpha AB. So then you can write the vector for alpha AB equals to alpha AB, which is this big expression. Okay, yeah, so that's your solution, radian per second square. I will not continue. I think by now you can see that the process is the same. We just substitute the value of alpha, and then you can use your calculators to find. So the key thing is what we don't know, we just substitute with a known vector, alpha ABK or alpha OAK, and from there we find the solution. So from here you can determine all the components of the solution by substitution. So I will just stop there to for you to do some thinking. So we have solved the equations or the questions that ask us to find what alpha OA is, alpha AB, alpha OA, and alpha AB, and from there you can find the acceleration of all other points. So it is quite straightforward from there. So I'll stop there for the acceleration. It has been a long lecture for you to get up to this point, but I guess by now you are able to solve the equations related to the 4-bar linkages, and we will do some more example later on for us to build up our confidence in solving the problem. Yeah, so we'll see you in the next lecture.